almost 10 years ago, when his hair was black and I didn't have a beard. Both of us have changed, hopefully for the better. Just to give you a very quick bio of Vijay's history so far, as I said, he started his higher education, at least in Pune. His alma mater is actually Ferguson College, which is same as me, except he did physics and I did chemistry. And from there, he continued to do a master's in Ferguson itself, and then continued to do his MTech from Pune University, which quite a few students have passed through here. So he has a long history with Pune. And after that, he decided, enough of Pune, I'm going to go to the mother nation of the UK. And then his PhD in university. That PhD was actually a part of the Marie Curie Fellowship, which is a very prestigious fellowship. So he got it for his PhD. And he worked with one of the stalwarts of atmospheric chemistry in UK called Paul Monks, who was one of his co-supervisors. Paul Monks, if I remember right, he's heading the UK government panel for climate change.
Yes, for last couple of
years. Yeah. So he's obviously worked with some of the best people in the world. But after that, he decided to go travel around the world. First went off to the US, worked in Kent State University, where he worked on aerosols, and then came back to India, worked in IIT Kanpur, and after Kanpur decided to go to Sweden to work on some lightning-based studies. So he's had quite a trip, but his true love was always aerosols. And after Sweden, he moved back to India and joined the University of Hyderabad, and has been working on aerosols, specifically on new particle formation, which we'll talk about today. In addition to all of this, he's also doing some interesting work on like heat waves, cold waves. So obviously, it's a very bright mind at work over here that can focus on lots of different topics. So Vijay, please go ahead and give your talk.
Right. Yeah. Thank you, Manav. That's so kind of you and very nice introduction. I hope I'm audible. Yeah, great. So yeah, first of all, I would like to thank Director IIT for the opportunity, and of course Vinu and his team, desk team, for all arrangements. So today, what I will be doing is I'll be talking about a topic which is kind of very close to my heart. From my early career, 2004. I always wanted to work on aerosol nucleation or atmospheric particle formation, but then, as Anup mentioned, I went to do PhD in satellite remote sensing. That I don't know why, but always, and I can say that it has helped me. So anyway, it was a good decision. So I'll be talking about atmospheric observations of new particle formation in India. And as we know that aerosols itself is a very wide research area. When we talk about aerosol physical properties, their optical properties, chemical properties, they have radiative properties, and there is one more property called as the dynamical properties. That's something which has been for some reason overlooked, especially in the Indian context. So my focus will be on the dynamic properties. And aerosol is something that we tend to relate to quite a few things around us. Air pollution, weather, climate, health impacts, and so on. My top outline is basically, I'll just briefly introduce what these tiny aerosol particles are and their climate significance. I'll just keep it to brief, maybe 1 or 2 slides, and then more focus on the aerosol dynamic processes, their theoretical understanding, followed by how do we detect and quantify new particle formation in the atmosphere, and their current observational understanding of NPF in India, followed by critical knowledge gap that we have in Indian context as well as global. All right, aerosols. Aerosols are nothing but the solid liquid suspended particles in the air. They vary in a wide size range with about 4 to 5 magnitude, 4 to 5 order of magnitude difference between the smallest and largest particles. And there are 3 known effects that I will not talk about much. So of course, direct effect, indirect effect, and there is also called as a cloud burnout effect. No aerosols means no cloud, because homogeneous nucleation of water vapor doesn't occur at ambient supersaturation, for which we need about 200% of supersaturation for homogeneous nucleation of water vapor. So no aerosols means no cloud. all these effects, direct effect, indirect effects, or even the cloud panorama, they all depend on the aerosol size or their mass and the composition. The best example is, for example, composition, the aerosol direct effect, whether it's a dust particle or sulfur particle versus the black carbon aerosols, which tend to absorb the radiation while the other tend to scatter the radiation. So these are the three properties that we must quantify in a way that we understand the strong spatial temporal variability that we have across the globe or over India. There are two types of aerosols, primary aerosols and secondary aerosols. Primary are the ones which are directly emitted to the atmosphere. It can be natural or anthropogenic, natural or volcano, sea salt or dust. Anthropogenic are the ones, biomass burning or biofuel fossil fuel burning. And we do have a secondary aerosols, which is basically referred as produced from co-emitted precursors. Because if you take any activity, not just aerosols are emitted to the atmosphere, but aerosol precursors are also co-emitted to the atmosphere. And these precursors can condense onto the particles. That cluster can grow in the atmosphere in much bigger size, which can be detected in the atmosphere. But there is what is called the Gibbs-free energy barrier on the aerosol nucleation, because nucleation itself decreases the entropy and enthalpy of the thermal system. So there exists a Gibbs-free energy barrier, which needs to be overcome in order for cluster to grow in the atmosphere spontaneously and detect. Okay. So the equation is given here. Delta G is equal to the first term, which is negative. So as long as this term is negative, so which means that as long as your system is supersaturated, LNES, the first term will be negative, which is a driving force for diffusion of vapor onto the cluster. So the cluster will grow spontaneously in the atmosphere. Whereas the second term, which is a strong function of the particle radius, RP, where if you have the small particle, the surface energy that is gained is more than the energy that is gained from the particle formation. Okay, so these two parameters are basically which decides whether the particle nucleation will take place or not, and this barriers has to be overcome in order for the clusters to grow in the atmosphere. So once a particular cluster reaches to a critical radius, and thereon it can grow spontaneously in the atmosphere and eventually can be detected and can even reach to the season sizes. So this is just example of this energy curves for the formation of neutral and ionic sulfuric acid water cluster, which could have maybe tens of sulfuric acid molecules and maybe 20 or 15 molecules of water. And there are, you can see that there are two pathways, pathway A and pathway B, where in pathway A you have a recombination cluster and produces the neutral cluster, and which is being evaporated because these clusters are not reaching to the size of critical cluster. Okay, whereas in path B, once the cluster reaches the critical size, it can spontaneously grow in the atmosphere. Then question comes, which favor contribute to the aerosol nucleation or leads to the aerosol nucleation? So saturated vapor pressure or high saturation vapor pressure substance means it's volatile. Okay, if you have more volatile substance, the molecule will dissolve readily from the surface. So in order to create a cluster or cluster of molecules, you need a vapor of low saturated vapor pressure so that molecule can stick together and form a cluster. So sulfuric acid has the lowest vapor pressure among all the vapors we have in the atmosphere, and that's why it has shown in the laboratory experiments like flow tube experiments or chamber experiments. Nucleation usually starts with the sulfuric acid. Only recent studies, you can see the 2019, where they have shown that highly oxygenated molecule with extremely low volatility organic compounds can also participate in aerosol nucleation and grow. But if you see other vapors like water, you can see very high vapor pressure. So as I mentioned in the very beginning, water vapor cannot nucleate it by itself, because for that you need very high supersaturation, 200% that we don't have, right? 101 or so in ambient. So water vapor cannot nucleate by itself. That's why aerosol is the key. Then ammonia or ethanol or formaldehyde, they are very high saturated vapor pressure. Okay, there have been several nucleation mechanisms have been proposed where two or more vapors can form a cluster. So we have what is called the binary homogeneous nucleation of sulfuric acid water, or we have a ternary homogeneous nucleation of sulfuric acid water, ammonia, We have a ternary emission of sulfuric acid water amines, and sulfuric acid can also cluster with organics compound. You just see the delta G. So this has the lowest delta G. So this thought to be a key mechanism that works in the planetary boundary layer. Where you have a lot of nitrogen containing compound and sulfuric acid from SO2. Basically, SO2 oxidized to form a sulfuric acid. Binary homogeneous has been well explained in the upper troposphere and lower stratosphere, whereas ternary homogeneous nucleation and sulfuric acid or organic nucleation works well in the planetary boundary layer, but which has not been validated extensively against the laboratory data. So there are a lot of uncertainties with these. There is, of course, there is also ionized nucleation, which also plays a role in aerosol nucleation. There are mainly two sources of ions. One is from galactose rays, and other is from the radioactive material from the soil. And these are all nucleation mechanisms that have been explained over the continental regions. We do have over marine regions where iodine and methane sulfuric acid can play a role in the particle formation. There is a lot of work on the iodine acid done in the past, and to some extent on methane sulfuric acid as well. This is just an example of a molecular dynamics simulation of a critical cluster. We don't have a definite size of a critical cluster. It can be anywhere between 1 or 2 nanometer or even 3 nanometer. Okay, so this is a critical cluster of 1.4 nanometer. And you can see we have different molecules, carbons and sulfur and oxygen and hydrogen and so on. Okay, now what happens after nucleation, right? So there are two processes by which these clusters can grow in the atmosphere. One is condensation, where diffusion of vapor onto these clusters. Another is coagulation, so which essentially means the self-coagulation of these small clusters, which can grow the size. Now, if you see this graph here, so let's say that you have a cluster formation about 1 or 1.25 nanometer. There are two possibilities. Either this cluster can grow up to 3 nanometer by further condensation, diffusion of vapor onto the particles of clusters, and essentially reaching to 50, 100 nanometer and essentially going into the cloud. Or all these clusters can be scavenged by the pre-existing aerosols. So if you have a polluted atmosphere, it is consider that it doesn't favor the new particle formation, because there are a lot of background aerosol particles which scavenge these vapors and which inhibit basically aerosol nucleation. But there is this picture on the right is basically analogy of American football game. So the red ones are your coagulators and the blue ones are your condensators, vapors. And you can see here also that what they have tried to explain that only a few clusters actually eventually grow in the atmosphere and become CCN and goes into the cloud droplet. So the real question is, what is the survival probability of this cluster? How long they can survive in the atmosphere, and what fraction of newly formed particles survive to reach to CCN concentration? But there are a lot of modeling studies which have been shown that about 50% of the CCN that we have in the atmosphere comes from the aerosol nucleation. But it has a very large range of uncertainties, start from 30 to about 80%. Okay, so of course, which is one of the area where a lot of work needs to be done. So it's basically the competition between the condensation growth and the scavenging by pre-existing particles that decides, or that is basically dictate their survival. Okay, and that decides whether the new particle formation takes place or not on that particular day. So essentially, atmospheric new particle formation is a two-step process. One is aerosol nucleation, and then followed by the condensation growth. NPF can increase the number a lot. You have rapid increase of number concentration, but mass probably little because they are very small particles, so they don't add up much mass. It occurs everywhere in the atmosphere, in all environments, forest environment or rural environment or urban environment. Even the mountain sides also see the new particle formation and so on. It is essentially a regional event, so you do have a local new particle formation, or nucleation itself is a very instantaneous process that can occur anywhere. But we call it new particle formation because it's a regional process that occurs over hundreds of kilometers and over a time period of 1 to 2 days. Okay, this is the very interesting slide and my most favorite slide. What you see here is basically I'm trying to explain how do we detect, and then followed by current characterization. So along y-axis, what you have is the size range, starting from 1 angstrom to about 1 micrometer. And then along x-axis, what you have is the time. And so basically what we need in order to detect, it's rather easy, I can have only these scanning mobility particle sizer. That is more than enough just to detect the new particle formation. But if I have to characterize, I need the information in this entire size range. So I need information in 1 angstrom for gaseous molecules, VOC, sulfuric acid, ammonia, and some of the oxidants like OH or ozone and so on. That we measure usually by PTRMS or SIMS. Then I also need the information in the cluster size range, that is sub 3 nanometer, where the nucleation takes place. So that we measure usually particle size magnifier or nano-condition nucleus counter. And then we also have what is called chemical ionization atmospheric pressure-induced TOF, which gives the molecular composition of these nanoparticles. Because we want to know what is the composition, what are the vapors of chemical species that leads to nucleation. Then essentially we need information is a wider size range from 3 nanometer to about a micron or so. That we get it from scanning mobility particle sizer and wide range aerosol spectrometer and so on. So if we put all together, this costing more than about 200 million rupees. So in order to characterize NPF, all you need is 20 crore rupees. Okay, so that's very easy task. So if you don't have 20 crore, then I think you cannot, you can of course characterize, but not entirely. You will give answer a lot of questions, especially the chemistry driving NPF. That is the most important question, because we need to know what are the vapors that actually leads to aerosol nucleation. So we need about 20 crore rupees. Now what you see here is you have a time here, and the diameter is on the y-axis, and what I plotted in the color is basically the number of particles. New particle formation is essentially a daytime phenomena. So you can see there is a burst of particles. Particle number rapidly increases right after sunrise, and the black line is mode diameter, which is nothing but the diameter of the peak number concentration. The diameter decreases right after sunrise. It's a dilution effect, and then start increasing over the time. So it's basically the particles are growing over the time. Okay, so these particle size distribution are looking like a banana. So banana plot are idealization of real new particle formation that's taking place in the atmosphere. So if you see the banana plot, then you can say, okay, yeah, it's a new particle formation. Okay, I'll give the example. So this is like a background day when there is no new particle formation. So you can see the mode diameter doesn't change much. It's pretty much constant during the day. The background aerosol mode diameter is around between 100 and 200 nanometer, or maybe 300 nanometer. And on new particle formation day, you can see there is a distinct change in the mode diameter and itself the particle size distributions. Okay. At the bottom, you can see I have plotted hourly average particle size distributions, and for different hours, 11, 12, 13, up to 17 hours local time. And you can see for all these distributions, the mode diameter is same. But for on NPF event day, the mode diameter at 11 or 12 o'clock is much lower, around 10 nanometer. And over the time, this mode diameter is actually growing. So you can see there is a shift in the mode diameter. So it means that particles are growing over the time. And the rate of growth is about 10 nanometer per hour. Okay. So essentially reaching about 50 nanometer or 60 nanometer. So here you have mode diameter of 30 nanometer. So you need a lot of high supersaturation in order for these particles to act as cesium. But you will probably need much lower supersaturation for 80 nanometer or 60 nanometer particles to act as a cesium. So new particle formation does have an implication for cesium formation. So characterization of NPF, yeah, it's a daytime phenomena, starts after sunrise. Because it's associated with the photochemistry, but there are 10 sites across globe where they found a nighttime new particle formation, which is associated with the photochemistry related to the ozone, mainly the ozone and some of the biogenic VOCs like monoterpenes. The first thing I want to know how frequently it occurs, right? So it usually highest in pre-monsoon. Of course, it's very obvious. It's a photochemistry associated phenomena. So higher solar radiation, there are higher chances that you will have new particle formation, and the lowest in winter. But again, this pattern is not universal. Then I really want to know what is the strength of NPF event. So how do I quantify it? By knowing the rate of formation of particles and their growth rates. So I do the particle formation and growth rate calculations. And then there is, of course, influence of atmospheric conditions, temperature, relativity, wind speed, and direction that has to be understood and quantified. So such characterization of MPF have been reported from India widely, except the chemistry, which is pretty much unknown. Except there are two studies where one of the study we actually found that sulfuric acid does play a role in new particle formation, which is not new, because it's known for almost last 2 decades. But yeah, it's kind of a first observation from India. And there's another study where we used AMS, where we found that nitrogen containing NPF unknowns because most of the things are known in a global context. Some of the things are still unknown in global context and largely in Indian context. So yeah, NPF, as I said, is the largest source of aerosol numbers and maybe aerosol mass. And it is expected to be less favored in polluted atmosphere because you have high concentration of pre-existing particles, which basically scavenge the vapors that participate in nucleation. So it is usually less expected in urban environments than the rural environments. But developing countries are becoming hotspot of NPF. NPF enhances cesium concentration by a factor of 0.5 to 11. So as I said, almost half of the cesium comes from NPF, new particle formation in the troposphere. So those are the modeling simulations with, of course, very large unsensitivities. In fact, we know that aerosol cloud interaction is one of the least understood forces in the climate system. It's mainly because of the ambiguity in the cesium concentration or cesium production. And the ambiguity in cesium production itself comes from the ambiguity in NPF, new particle formation. Because as I said, there are several mechanisms proposed, but we don't know which of the mechanisms is dominant in which regions. And the primary emissions, we have strong spatial temporal heterogeneity across India, across globe. Then again, their role has to be quantified. And then the growth rates, that is heterogeneous, where the vapor condenses onto the particle and whether that lead to the cesium formation or not. So these are some of the things which are not really quantified, and there is a lot of ambiguity. That could be the reason why there are a lot of uncertainties in cesium concentration and therefore the aerosol cloud interaction. So in all, NPF has a critical importance for climate studies, and since it's a source of large number of ultrafine particles, so it could have an implication for human health. This is just a map. I mean, they do not have all the study here, but you can see there are a lot of studies over Europe and America and China, and there are some studies over India also, Ranichari, Mukteshwar, Mahabaleshwar, of course, Pune, and so on. It has been extensively studied across the globe. It was reported, first maybe in early 1960s. Even prior to that, 1884, Atkin was the first who actually comes with the instrument for measuring of nanoparticles. So that is way long back. But new particle formation is terminology came only in 1960s or so. In India, it was reported in 2005 by Chate and Devra. That was the first study from India in 2005, and then subsequently we had several other studies. So yeah, this basically leads, and there are now altogether only 25 published articles in entire Indian literature on new particle formation specifically. So we have studies from urban, we have from semi-urban, urban coastal, semi-rural, mountain, remote background, and mountain semi-rural. We also have one cruise measurements from Bali group. Very recently they have published from the cruise measurements. This is map showing just geographic distribution of different sites across India where new particle formation has been reported. So Hanle, Ranichari, Mukteshwar, Delhi, Kanpur, Hyderabad, Northern UT, and so on. Solapur, Pune, Mahabaleshwar is also there, and of course Trivandrum and Ankara. In the background, what I plotted is basically the Modi circuit neighbor. So you can clearly see the Ooty and Hanle looks like a very remote location, where the particle formation is again very rare. But Delhi, Kanpur, or Pune, and Hyderabad there are moderately to heavy polluted environments where new particle formation have been reported. One thing you can also see that there are not many measurements in rural areas except Gadanki, for example. So we don't know what is happening in rural regions as such in Indian context. Okay, then I had a question. I mean, we have a question like how frequently does it occur? So I have data from about 6 sites here. So the blue bars are nothing but the days when new particle formation has occurred. The red ones are the days when it has not occurred, and the green ones are undefined. So forget about it, because there will be some days where I will not know whether it's a new particle formation or it's a background day. It's not even background day. Maybe there's something else. Maybe there's biomass burning. Somebody has burned something, so you just see suddenly increasing aerosol number concentration, which is more than the background concentration. So along x-axis you have different month. Along y-axis you have percentage of UL days per month. So and then you have this is Ranichori, Mahabaleshwar, Trivandrum, Delhi, Hyderabad, and Vijay. So what you see that you have more blue bars in urban areas. So that is you have more frequency of occurrence of NPF in urban areas than the rural areas or mountain regions. I should not say rural because we don't have many of rural areas except that. But in mountain regions, these are high altitude mountain regions, Ranichori, Vishwar, or even Mahabaleshwar, new particle formation doesn't occur that frequently. Okay? But it does occur, but not as frequently as in urban areas. This is so it does occur in urban areas, but this is one of the study from Gadanki, which is a ruler. This is based on about 3 months of data during April, May, and June, where we observe new particle formation infrequently. And I just listed down some of the processes that trigger NPF. So first one is chemical species, which is very important. We have to have enough vapor concentration for nucleation to trigger. The secondly, conditions to sink. So pre-existing aerosols should be lower so that vapor have less scavenging. Then there should be more condensable vapor for particle growth, and then again atmospheric condition. So this is conditions in sink, CS, and this is RH, temperature, solar radiation, wind speed, and wind direction. The rate, these are the diagonal variation of all these parameters. The red line is for non-nucleation days or non-NPF days, and the blue ones are NPF days. So what you see that there is not much difference among all these parameters. So only difference what we found is in the chemical spacing, that is SO2. SO2 is very low in Gadanki compared to Delhi or Kanpur. So what basically we concluded here that because of low SO2, the new particle formation was frequency was lower. And again, second finding was that we had a measurement during June, so which was kind of cloudy conditions as monsoon started approaching. So that is another reason why new particle formation was infrequent in Gadanki under reduced photochemistry because of the presence of the clouds. While it was observed infrequently in Gadanki, we observed commonly in urban areas like Kanpur and Pune. This is a study of collaboration between IITF and Kanpur back in 2012 and 13, where we do see difference in CS and temperature and all other parameters for both the sites. So you can see conditions in sink. The red line is again non-NPF days and blue is NPF days. So CS is lower on nucleation days and higher on non-nucleation days, which means that you have lower conditions in sink on nucleation days. So you have lower pre-existing particles. And temperature is higher, or solar radiation is higher on nucleation days. So you have more active photochemistry than the non-nucleation days where the solar radiation is slightly lower. Now in this figure, what I plotted is one is a sink along x-axis, and along y-axis is basically source. So solar radiation into SO2. This is nothing but the condition sink. And what you see, and the dotted dots are basically NPF days, and the crosses are non-NPF days. So if you see along this line, you have a pretty much same source, but if you see vertically, you have more non-nucleation days when the condition sink is more. Okay. So source is, of course, it's basically a combination of both source and condition sink. But even the source is same, the nucleation will not occur if there are more pre-existing particles, because whatever vapor available is actually scavenged by these pre-existing particles. Okay, so that is, so basically it's a competition between the source and a sink that basically decides whether any particle formation will occur or not. Okay, this is another very interesting study, and COVID-19 lockdown, did give us a very good opportunity to detect and attribute anthropogenic influence on different atmospheric processes. So this is one of those, and I started measurements from mid-April 2020 during peak lockdown time. I got the special permission from our university, and I used to go to lab every day for the observations. So what you see here, the time series of particle size distribution from 15 April to about 31st May for lockdown periods, that is 2020. And this is business as usual for 2019. So for the same period, but for different years. 2019 that is business as usual, and 2020 lockdown. And I use two different instruments. One is SMPS, and other is nano condensation nucleus counter, which gives the particle size between 1 to 3 nanometers. The first obvious observation is you can see the color contrast, change in the color contrast between the 2019 and 2022. So of course we had a very low concentration of aerosol due to reduced anthropic activities during lockdown, that you can clearly see. What is interesting is you can see the bottom plots here in both. You don't see much change. So aerosol nucleation was not suppressed as such. So aerosol, because that is what we see. We say that nucleation is more favorable at lower pre-existing particle concentration. So that is in rural areas than polluted areas. So that basically proves here. So it was more significant than in case of the polluted environment 2019. But the problem was there was not enough vapors in the atmosphere which can condense those particles into much bigger size and eventually can be detected. So what we found that the new particle formation frequency was threefold lower during COVID-19. So usually 2019 we had about 47% of days new particle formation occurred during this period, while only 15% occurred during this period. There were particle bursts, but those particles did not grow large enough to be detected in the atmosphere or to be detected by the SFS. We also tried to address what are the different reasoning we tried to do. We first looked at the what is the ozone sensitivity, and of course India falls in NOx limited regime, so that could suppress the ozone formation. And we did look at the I don't know if it is visible, but ozone concentration was lower during the COVID-19 compared to the 2019. And the temperature was also pretty much lower by 2 or 3 degrees Celsius during 2019. So both are major oxidant. So we had reduced oxidation extent of the atmosphere in 2020. So that could be also reason why there were not enough vapors for condensation onto the particles. This is one of the instruments. This is first and only available in India. Nano condensation nucleus counter, or we also call it the particle size magnifier, which gives the particle size between 1 to 3 nanometer. The beauty of this instrument is you can get the critical size of the cluster, and you can also find out their formation rate. So that is what I plotted in along x-axis. J is nothing but nucleation rate or formation rate of 1.4 nanometer particle. And along y-axis is their number concentration of sub-3 nanoparticles. And in the color, what I plotted is the sulfuric acid proxy. So we don't have measurements of sulfuric acid as such, but we can calculate sulfuric acid proxy based on SO2 measurements. And what you see that there is very good positive correlation among all these three, and we can compare with other sites across the globe wherever PSM measurements are available, and which is quite well matching. So this is Kent, where that's the ruler site. So of course you will expect the lower formation rate and lower number concentration. This is the China, where you have very high formation rate and high concentration. So this basically here we concluded that sulfuric acid does play a role in the aerosol nucleation. This is another study where we used AMS data, but we did not look at sub 100 nanometer, that is ultraviolet particles. Rather, we looked at the entire sub-micron range, between the nucleation days and the non-nucleation days. So on nucleation days, what we found that we have more freshly oxidized organic aerosols, which comes mainly from the combustion. So we did a source apportionment and we found there are more hydrocarbon-like organic aerosols. Then we looked at the mass spectra and what we found that there are more more signals from the nitrogen-containing compound, like amines, C2H4N, or more common is CHN or C4H. So we concluded that the amines could also play a role in the new particle formation. As compared to non-nucleation days, the intensities were very low, but on nucleation days, the intensities were very high. Then later we also looked at what is the survival probability of these new particle formation, newly formed particles. What fraction of these particles can reach to sizes of cesium, 50 nanometer or 100 nanometer. So 50 and 100 nanometer are proxies for cesium. So we took that and 50 and 100 nanometer, and we calculated the survival probability of 50 nanometer and 100 nanometer based on particle size distribution measurements. And it is calculated by simply taking the ratio of their condensation sink, so that is source for the growth, and their coagulation sink, that is the sink for these clusters. And what we found here in Ranichori that survived to 100 nanometers. So roughly we can say half of the newly formed particles probably survived to cesium sizes 50 or 100 nanometer. But I must say that there are a lot of uncertainties in these estimates that one need to be considered. Then we extended this work to which is entirely based on measurement rather than using some kind of model. And there also we found that there is significant increase in cesium 100, that is 100 nanometer, during the NP21 days. So cesium increased by 100 to about 200%. So that is quite significant, and we found there is more increase in urban areas than the mountain background site. So we kind of concluded that the urban areas could be a significant source of cesium or NPM. Then we of course looked at the what is the spatial extent of NP, because as I said, it's not a local event; it's a regional event, and from weather or climate point of view, we need to know how widely it is occurring and what region. So we tried to use a high split model. We used here basically high split model and calculated the spatial extent of new particle formation events, and for different seasons for Hyderabad site. And basically this just shows the direction of the air mass from where it is coming, and possibly the end point of this particular field contours, that's the point where new particle formation started within the air mass, because air mass is a huge body of air that's moving in the atmosphere. And one of the crude assumptions that we have is air mass is homogeneous. Then only you will see new particle formation. If you have heterogeneous air mass, then you will probably not see new particle formation. So we found that NPFs occurs over spatial fields of hundreds of kilometers and a temporal scale of 1 to 2 days. It is something that it's not like unknown. It's again known, but something that we were really very curious to know what really happens over in the context or over at the Hyderabad site. Now the real question is, when does it occur in fluidic condition? That is something in general we have characterized. We know at what condition it does occur and at what condition it does not occur. But why do we have those conditions on certain days, and why do we have those conditions on other days? Like in NP may occur today but may not tomorrow. So what is different between today and tomorrow? So that is basically the question. This is one of the review paper where we have summarized our understanding. And there are about 12 sites where researchers have reported the nucleation of formation rate of new particles and their growth rates, and we just try to correlate how they look like. Okay, so if you see the daily, so basically the size of the symbol tells you the condensation sink, and the color is different site type, argon or semi-argon and so on. Now daily, if you see, which has the highest formation rate and highest growth rate, but it's also severely polluted as compared to Kanpur or Pune or Solapur. Okay, but still NPF does occur, even it's severely polluted. Okay, and Kanpur is more or less same. Even you see the size of box dot is basically you have higher consistency. So even at higher consistency, new particle formation occurs. So it's not just whether you have more pre-existing particles in the atmosphere. It's a combination of both pre-existing particles and the vapor which decides when new particle formation will occur. This is just similar kind of a plot where we looked at the consistencies and the growth rate where or moderately polluted or rural. So this graph basically tells that it doesn't occur really in polluted environment. It occurs in moderately polluted environment, which means that even it's a polluted environment, there might be some days when atmosphere is unstable or you have maybe more ventilation, which create a kind of a moderately polluted environment. And that's the day when new particle formation occurs, because it doesn't happen that frequently also, right? In a month, probably 10 days. So you may have unstable situation on 10 days during a month. So this is the hypothesis that we are working on now. NPF in polluted environments occurs when air is sufficiently diluted. So it does occur in urban environments, but only when the air is sufficiently diluted, which means that you have lower pH in particles. So you have lower loss of vapors onto the particles. So there are more chances that particle will inflate, and then they will go eventually in the atmosphere. So this is something that we are working on now. So in the review paper, we also identify some of the critical knowledge gaps on NPF, especially in Indian context. So something like chemistry driving new particle formation, which is kind of overlooked. Then what fraction of newly formed particles reach to cesium sizes? That is something again, and then of course, what is their cloud forming potential? That is something is unknown, in the global context. Then to quantify the relative contribution of VOCs to NPF and thereby CCN. So you have biogenic VOC, anthropogenic VOC. So what is their role? Okay, especially over the forest when you talk about the biogenic VOC, or in urban environment, role of anthropogenic VOCs. Then the relative importance of NPF to haze formation and the air quality and climate interaction. Okay, so what is their role in the haze formation? Because we have, as NPF is the largest source of aerosol numbers to the atmosphere, even though the sizes are small. But what if all those particles, survive and grow to 100 nanometer or 500 nanometer? So that can lead to haze formation. And then, of course, then one need to understand how air quality and climate will interact, because, in my opinion, these are two different entities, and one need to understand how they interact and what are their feedback. So just a concluding remark, as I mentioned, aerosol cloud interaction is one of the least understood process, and most of the ambiguity comes from CCN. There may be other factors, of course, but yeah. The ambiguity in CCN mainly comes from the primary and secondary quantification. So what we probably need is regional model simulations with parameterized aerosol nucleation schemes based on the cloud chamber studies or laboratory studies to understand the aerosol microphysics on a regional scale, and then eventually to estimate the cesium production from NPF. Then, of course, the chemistry dynamic secondary aerosol formation is linkage to cesium formation, and its implication for haze formation are something that is being largely unexplored over the context. So what we need is highly spatially and temporally measurements of particle size distributions for developing a superior process level understanding of evolution of aerosols in the atmosphere. Of course, that we have most of the location across India, mainly the urban regions. But what we also need in rural locations, where I hardly see that we have any particles number size distribution in rural locations. So my research at Eminence Hyderabad is funded by Science Engineering Research Board, Department of Science and Technology, DRDO, not onto the NPF studies, of course, but other aspects of aerosols, their physical properties, UGC, and institutional details. This is my small group at University of Hyderabad. Yeah, one of them is I don't know if you see the gap there, but yeah, he's a doctor now. Evan Thomas, he's in Finland, and one or two other will submit thesis space. Yeah, so with that, thank you so much for your kind attention, and I'll be happy to take
Yeah, thanks a lot, Vijay. Very interesting talk, some exciting results over there. Can we throw it open to questions? If anybody has a question, please feel free to ask.
Hi Vijay, it's a very interesting talk. So are there any publications showing higher frequency of occurrence in rural environments? Because in India there were some measurements, but some are like not reported, even in the CAPEX. So we had some observations in Mahbub Nagar, which is
I remember that. Right?
some good events, but I think we never reported.
And if you remember, there were you have NPIP based, consecutive NPIP based actually.
Yeah.
Almost a week or even more.
Because one of the conditions we say that the pre-existing aerosols should be lower.
Correct.
So which is not true in urban environments. Still, there is a good number of events occur in urban environments.
Yes.
Then if that is the case, in rural environments, if there any reports showing higher percentage of occurrence?
There are. If you see from Finland, papers from Finland or Europe, there are a lot of papers which show that there is more frequency of NPF in rural environments, but most of them are from forested region. So especially if you go to the rural forest, where you have a lot of monoterpenes, and the frequency of NPF is very high. But if you come to the urban areas in European countries, where you have a lot of pre-existing particles, the frequency reduces. But in Indian context, I don't think we have a site where we have a continuous measurement, except Gadanki. But Gadanki, unfortunately, we happened to measure during May and June. So June was something like the monsoon onset. The photochemistry is not so active, so we can't expect anywhere any particle formation. But if you could have a year-long measurements from rural locations from India, that would give some idea. Mahabaleshwar, of course, we have, but that's again mountain semi-rural site. So, but there are reports, yes. Thank you.
Any more questions?
It's a nice talk. So I wanted to know that in one of your slides you showed regarding the role of amines on NPF formation. So whatever amines that are being emitted in atmosphere, it's mostly from maybe from biomass burning, something like that, right? And those are having high vapor pressures. So how you can relate those high vapor pressure molecules to help these newly formed particles to go into particle level, like detectable level?
Yeah. So as I mentioned during the
talk, and also just another thing to add, because this AMS, it doesn't measure below 70 nanometer.
That's what I said.
So how you'll be like correlating that, and just to say that the amines are definitely playing a role, because there may be some emissions that are contributing to these amines, because we'll be having after some time some observations, right? After increase.
So as I said in the talk, when we talk itself, that what we did was we looked at the chemical composition of submicron aerosols between the NPF and non-event. So I don't know actually which species is contributing, but what we saw that on NPF days, we have more amine-like species than non-event. So that resulted that there is a source of amines from maybe vehicle emission, because we found more HOA-like organic aerosols. We did source apportionment, and we found more HOA. So it's not biomass burning either. So it's coming from vehicles. And one more thing is, we are not saying that amines playing a role in the nucleation or growth, because we cannot with the AMS. What we're saying that we have more electricity intensity in submicron particles during NPF days. So possibly they have contributed either in the growth or nucleation. But if you see the previous studies in the literature, where they have shown that amines do play a role in aerosol growth mainly, but not in nucleation, or even ammonia. They play a major role in the growth, because let's say sulfuric acid particle, which is acid, right? Amine is a base, so you have acid-base reactions, so there's more chances of amine condensing onto
the hydrogen oil.
Yeah.
So another thing, what you observed in Mahabaleshwar, so whether the frequency of NPF is higher in pre-monsoon or?
So this is just 1 year of data. So I mean, I wouldn't really make a statement based on 1 year of data. We need to see, maybe 5 years or 10 years of data. Then we can say, okay, for Mahabaleshwar, your highest frequency monsoon. Generally, we see highest frequency during pre-monsoon, and we know the reasons also. But for Mahabaleshwar, this is 1 year, and you can still see highest frequency in pre-monsoon.
No, why I wanted to add, because we do see a lot of isoprene emissions
Yes.
during pre-monsoon because it's a forested site.
Yes. Yes.
And isoprene is a well-known suppressor of.
Yes. I do have a picture.
So that's why actually I'm just wondering.
So if you have more isoprene, depends upon how much ppb you are talking about, whether 1 ppb or 10 ppb.
4 ppb. 4 to 5.
4 ppt or ppb? ppb. So 4 ppb is still not much, I would say. 10, 15 ppb is like something very large isoprene emissions you have. That could definitely suppress new particle formation because it has to oxidize several times, and there is not enough OH. Then it will not, subsequent those oxidation will not occur, and maybe other VOCs will not be left with, for oxidation. So basically, oxidation extent will be lower if you have more isoprene. I don't know how much isoprene is there at Mahabaleshwar, and because this is not forest environment, right? You do have a lot of vehicles coming in there. So of course you have a lot of SO2. So if not is isoprene, maybe SO2 or NO2 or ammonia might have played a role in the new particle formation. So we published one paper from Michigan Forest where we don't have any anthropogenic source, where we have only, it's a widening environment where we have a lot of isoprene, 10, 12 ppb, and we found only one event in entire 3 months. And same for Amazon. Amazon also, you don't see any new particle formation event. There are 2 reasons. One is it's a very rural and there is a lot of ice. Yes, sir.
You had some observations during lockdown period.
Yes. But the frequency was
there any different from what we observe in normal atmosphere?
The intensity was lower. Intensity of banana plots was lower. Intensity of particle formation was lower compared to the business as usual.
What was the instrument you?
Scanning mobility particle sizer, and I also had a nano condensation nucleus counter. So I have plotted here, actually, I don't know if it's visible or not. This is the formation rate between 2019 and 2020, which was more or less same for formation of smaller particles. When we smaller, less than 3 nanometer.
Oh.
But when you look at the growth between 10 and 25 nanometer, the growth was higher during 2019 and the lower during 2020, which means that there were no enough vapors available during 2020. So the intensity of
We made some measurements. We found that
I saw your
this particles in the range of 1 to 3 nanometer, they were so low or even absent sometimes.
Okay.
And somehow instead of growth, it's like a banana type event.
Okay.
It was a kind of shrinkage of higher particle.
Yeah.
25 nanometer or so, and the shrinkage you observe regularly, but the growth is not so regular.
Yes, because there are low vapors, and there could be 2 reasons why you have shrinkage. One is you have a diffusion of semi-volatile kind of compound.
No.
With the day progresses, temperature increasing, that vapor can evaporate, the semi-volatile what contains. So that could be reason why you have growth increasing and then shrinking. So particle size is reduced. So that could be the
yeah, that's what ultimately we had to put.
Yes.
Because one of the objects.
Yeah, that is also very rare sight.
That inorganic things, they don't have such vapor pressure, they will evaporate.
Correct.
But organic vapors, carbonaceous, they can evaporate and give rise to that. Because there was continuous evaporation type of reduction type of thing.
Yes.
And that was kind of supported by some chamber experiments from NASA.
Yeah, think Mahabaleshwar also has seen 1 or 2 such events where they have observed shrinkage. And it's anyway rare actually across the globe. There are hardly a couple of papers on shrinkage event. So still something that I mean I don't have clear-cut explanation why.
Yeah. And one very basic question, I mean, might maybe kind of foolish, but most of the places you are observing this banana type events in the morning.
Correct.
When temperature is rising.
Yes.
But at the same time, solar radiation is also rising.
Correct.
Both are.
After sunrise, yes.
So sometimes I wonder what is the main is it solar radiation or temperature? Because temperature, if you go to cooler countries, their temperature will be rising, but it will be rising.
So it's the main solar radiation. Simple answer.
Radiation.
Now, because of solar radiation, right after sunrise, you have sun energy coming to the atmosphere surface is heating up. You have boundary layer is elevated, so you have more dilution. So whatever aerosols they were at the surface, they are elevating up. So you have you're creating environment with low aerosol at the surface. So instead of those vapors condensing onto those particles, they will start nucleating after sunrise. So temperature, of course, is very important because it's a photochemistry associated event. When you have SO2, it's not going to nucleate. It has to be oxidized to form sulfuric acid, and then it will nucleate. Same goes for the VOC. So, but it happens only right after sunrise when there is enough dilution, and that's the reason why more diameter goes down. And so it's a dilution effect. During night, you see more diameter around 100, 200, 300 nanometer. But right after sunrise, it goes down because you have dilution. Most of the particles are elevated up.
Also OH production.
OH production, of course, yeah. And then subsequently all things follow. OH production and then ozone formation you have during daytime that peaks during noon.
So yeah, increase in those atmospheric temperature and solar radiation, it's rising every day.
Yeah.
But every day you don't observe events.
We don't observe every events, but every day you don't have clear sky also.
You have cases are not present.
I mean, as I said, it's like events occurs around 10 or 12 days in a month, and not every day is the same. Like compared to today, I don't think we have. There is a lot of change in terms of emissions between today and tomorrow. So, what is changed between tomorrow? Function occur and tomorrow it did not. So it's basically whether atmosphere is stable or unstable. If you have stable atmosphere, maybe you have homogeneous air that's moving, and then probably you will have neo-particle formation. If it's unstable atmosphere or there is a cloud, then of course it will affect your photochemistry.
Is there any quantitative study of that output that I agree with you, but
there is no, but that's what I'm actually working.
There is some quantitative quantity that is critical.
No, I know the solution also, but I don't want to give it on here. Sorry, I'll discuss with you. But yeah, we are working on this paper and we have some hypothesis. So I'll discuss with you definitely. But that's not the probably entire story. There could be several factors that decides when new particle formation will occur and when it will not. And as I said, it's not just because of atmospheric conditions, it's a vapor, background particles, and then of course
maybe some combination.
Combination. So it's a balance between all these parameters that decides when it will occur.
Any more questions?
I do have I just want a little more explanation on you have done the back trajectories, right, to see the spatial extent of the
yes.
Could you explain how you did it? And
so we calculated, of course my student did, but yeah, I know how we did it. We calculated hourly air mass back trajectories. So let's say my event starts at 10 o'clock. So that is my end point because I am at the site. Start time is 10 o'clock, so that is my end point. Then next hour, 11 o'clock, I'll go 1 hour back. So I take endpoints of each trajectory from each hourly trajectory, and then you get the points. So that is possibly you are tracing the air parcel backward in time and spatially also. So there is a very good paper I can share with you if you want. I can just drop me email or something. We just followed that methodology. No, nothing. So there are only two ways you can find out the spatial extent of NP. One is you have measurement at different sites in a air mass. If you know like from where air mass is coming for a particular city, you can look at the climatology, and then you can have sites and then see whether NP occurring at each and every site. That is one way, which is very expensive and not possible also. And this is the second way. You trace the parcel from where it is coming, and it's not the source of parcel that decide whether NP will occur or not. Okay, because you may have the same source between today and tomorrow. Today may be NP, tomorrow may not be. So it's not the source again. So we just should not do blindly, air mass trajectory and then say that this is not NP. That's what I have been doing also, to be very honest. And I feel that I probably that's not right.
Very nice presentation, Gaurav. Couple of doubts. First, about the banana curve. Would you read the reduction in mode diameter as the indication of NPF, or would you as dilation?
It's the same thing, but I need reduction in mode diameter. Yeah. So that is basically because of dilution.
But then the mode radius is the one which has maximum numbers. So we are talking about the numbers here, not the concentrations.
Yes, because you may have a bimodal distribution. Right. What I'm looking at the mode diameter of the peak number concentration, not all the modes.
Okay. And the other thing was, I remember the few of the last slides you talked about ICAP data being comparable to what's happening over Delhi.
Yeah.
What was the wax? I just forgot the wax is there.
Not really comparable. ICAP is somewhere which is probably it's there.
The wax is yeah. So would you want to spare a thought on this? How
I'm not actually comparing here between the sites because that will be wrong because each site is different, right? Urban and as I said, it's not one parameter that dictates the NPF. It's a balance between both the parameters, or rather three parameters: formation and growth and conditions. So first, I'm not comparing between the sites. Secondly, ICRAB we see more formation and more growth. It simply means that there are enough effort for formation and growth, and because you have very probably less space. So over the marine regions.
Okay, so the last question is, how far are we from some sort of parameterization, putting these all things together and getting an FPA in the models?
Doesn't ask simple questions.
So I don't want to give any timeline. So I wouldn't give also because it may happen within 1 year.
Teaching there, I believe. So
yes.
Put those things together.
Yeah. So we don't have many modeling studies as such. But we have expertise, of course. I know few people across India, they are doing aerosol microscopy modeling. And we also understand, we need to also understand that it's not easy to do these kind of microphysical simulations, for example, or regional models like GeoScale or WRF came. So that is one thing. So parameterization, I don't know. I don't want to get into it. But yeah, we are probably heading towards it.
One of the main things missing is the chemicals.
Chemicals, yeah.
Any more questions?
Can we say SOA formation is also kind of?
It's a heterogeneous nucleation. Yeah. SOA formation is also nucleation. Heterogeneous nucleation where vapor condensing onto the particles. We say SOA because more is organic, right? Secondary organic aerosols rather than secondary aerosol formation. When I say secondary aerosol formation, I'm taking account both SOA as well as the homogeneous nucleation. And it's nighttime because it's mainly a growth. Right? During nighttime, your boundary layer is very shallow. Especially, let's say, you take an example of northern India during winter time. You have very colder condition, boundary layer is very shallow, temperature inversion. There are a lot of vapors in the atmosphere anyway, biomass burning.
Nitrate chemistry is strong.
Yeah, I'm on here. So, and then you have a lot of vapors in the air that can condense onto these particles, pre-existing particles. And you have very stable condition, right? Whatever you actually emit, it doesn't go anywhere. You have very less ventilation. The wind speed is down. So that's a perfect scenario, like to make a cocktail of air, where these vapors can condense and you can have a SOA formation. And new particle formation will not occur. New particle formation doesn't occur in Delhi in winter time, that I can tell. And no one has it outside.
But
what we observe is the growth.
Other locations you've observed.
Yes. So difference between growth and new particle formation is, when we say new particle formation, we have enough confidence that particles are newly formed. So there is a significant number of particles less than 25 nanometer. So those we call as a nucleation mode particles, and those are the particles more likely come from secondary source, not from primary source. But we do have a banana shape for particles which are much bigger, 50 nanometer, 100 nanometer, they are growing even up to micron. They do upper banana kind of stuff, but they are not new particles. They are a primary particle which are growing in the atmosphere. So those are SOA, what you are referring
to. I have just one imaginary question. If there is no ammonia in the atmosphere, like low ammonia conditions, so whether the particle formation will occur or not, which gas or which reaction will be crucial at that time?
If there is no ammonia, it will still occur because you have a lot of organics, volatile organic compounds, and we even don't know what are all these organics present, right? Because some of them we can't even detect. There are secret terpenes which are present in very pptv level, 1 to 2 pptv. And I don't think we have PTRMs going down to below PPT. So there are lots of organisms that are present. So of course, new particle formation will still occur.
And amines can contribute.
Amines can contribute also. Yeah.
Thank you.
Okay. Any more questions? Vijay, I've just got one. So during the talk, you mentioned one very interesting thing, saying developing country, urban areas are becoming hotspots. Yeah. Why not developed countries?
Why not developed countries? Because probably they have lower pre-existing particles or lower strength of emission.
If there's low pre-existing particles, then they should become.
But there has to be enough vapor also. It's not just the pre-existing particles. There has to be enough vapor for particles to nucleate and nucleate some group.
But are the VOC concentrations that much higher in Indian urban regions as compared to?
That is an interesting question, but I never compared like that. But of course, they are not that high compared to developed countries. Even if you take, for example, SO2 or NO2, the levels are much lower than China. And that statement actually came from the Marcus one of paper.
Because that makes me think that it's sulfur that's driving it rather than VOC.
Yeah. But I'll give a very best example. 1952, we had a smog event, right? June 1952 in England. It is mainly was sulfate erosions, right? So if you have more sulfate or SO2, then of course we will have a lot of new particle formation. And we do have sulfate in urban environments, right? If any of the city which doesn't have much SO2, for example, then probably they will not have much. VOCs are there, of course, but I don't see there is much differences between different cities in terms of VOCs. Yeah, except you go to the forest environment compared to the urban environment.
Great. If there are no more questions, then can we please have a round of applause and thank you. And there is some tea organized in the room opposite, so please stay behind and feel free to chat to Vijay.